Swayam Prabha. Digital India. Educated India.
Yeah, then welcome to this Gaian course on high fidelity lattice Boltzmann methods. We'll start first with a little bit of low-level introduction. In the afternoon, we have the second lecture where we talk about a little bit the kinetic theory, which is one of the many roots of the lattice Boltzmann method. Yeah, the lattice Boltzmann method is a method that has several roots. Yeah, like the banyan trees on this very nice campus. So I don't know what your background is, but I guess that most of you are interested in the application of lattice Boltzmann as a tool for doing high fidelity, in this case, fluid dynamic simulations. This is actually not really the way lattice Boltzmann started. Lattice Boltzmann, by a little bit a different name, started already in the 1970s, even before I was born, as an idea of lattice gas. And here it was not so much about doing actual high fidelity simulation of fluid dynamics, but it was more like the question, what minimal system would you have to use in order that on a larger scale you see the emergence of fluid dynamics? Yeah. So we tried to minimize the nature by saying, okay, suppose space is just a distribution of points, yeah, and there are particles that move in between these points. So say we'll have at this point here, and there would be a particle going here, or the particle could go there, particle could go there, and particle could go there. And then we have, this is their speed, and according to their speed, we make a time step, and in the next time step, the particle will just have moved according to this line. So it's jumping one lattice node at one time step. Yeah? And this is something that we then call streaming. From node to node. So, and this is of course not enough in order to describe how matter functions, in particular flowing matter. Okay, I should potentially say, so these things here are the speeds. So, okay, this moving around of particles along these lines is of course not enough. And there was the idea of collision. So we have streaming and collide. Okay, then I write colliding. Streaming and colliding. And we can see this like this. So on a node, particles arrive, for example, like this. And from kinetic theory, we know for a very long time, since Boltzmann, or this was his assumption, that only collisions between two particles actually matter. So it's very rare that you have three particles hitting at the same time each other, right? So we can actually reduce things to binary collisions. And now when you have a binary collision like this, what they could do is they can bounce just off the same way. Then you could say nothing has happened, right? Or, just you have exchanged the one particle going to the left with the one particle going to the right. However, we treat all particles the same. So it didn't actually change anything. The only way that you change anything is if the particle goes out of, these particles go out of this line. This is now what you have in the collision. So particles change direction by obeying conservation rules. So conservation rules means there are some possibilities that cannot be changed. For example, say you have only one particle arriving on this node, yeah, then it has to go out the same way, otherwise it would not conserve momentum. Yeah, and the same thing is if you have particles like one particle arriving this way and one particle arriving that way on the node, then according to the conservation of momentum, you would also have not changed them, right? So, question, is this enough? So this was the first question. Is this enough to actually recover fluid dynamics when you make this, when you make this in a very large system and you repeat it over and over again? Will this be enough? Who believes this is enough? Who believes this is not enough? Who understood the question? So, I mean, every human being has the right of not having an opinion, right? Sorry for being childish. These guys, this is Nabla, so he is always. I have Nabla giving answers and Laplace asking questions. Yeah, so this is my stupid, childish style of doing lectures. So so from this, fluid mechanics does not emerge. And the reason why it's not emerging is because there is no diffusion of momentum in this thing. If you think about this, momentum cannot move perpendicular to its own direction. So in fluid dynamics, we of course observe that there is diffusion of momentum. Yeah, it's called viscosity. This is not possible with this model that they were using in the 1970s. So, but then in the 1980s, they had a little bit a different idea, just putting these lattice nodes in a different position, and now I have to be, so this is not accurate. I'm just guessing where these nodes would be. Okay, so instead of this Cartesian grid that you have, where particles go in straight lines, horizontally and vertically, they had the idea of having a hexagonal lattice where you have speeds like that. So as a hexagonal, I mean, it's all in 2D, by the way. And the hexagonal lattice can actually do the job. So just changing from the Cartesian lattice to the hexagonal lattice, it was observed if you do the same thing, streaming, colliding under the conditions of conservation, yeah, and you zoom out, you do this on a very large system, and you average this over a long time, you observe that you get fluid dynamic behavior out of this system. And a little bit the confusing reason is that this kind of three-particle collision, remember I just said that in the original kinetic theory, we only count binary collisions, actually, yeah. But these binary collisions, they could not move the information out of the single line. Here, a collision like this, when particles move like this, so you would see the momentum. So you see that these two black arrows, they carry some momentum in x direction, where x is the horizontal. Yeah, so they have a net. So because it's not exactly twice, but they have more momentum than the one that is going here. And now if they do this triple collision, where they are returned back to the outside, they would spread, they could move momentum in the horizontal way in the vertical direction. So this is important in order to get fluid mechanics going. So here, momentum can move out and spread, say laterally. Okay, so this is a little bit of history. Now, you didn't come here to learn about lattice gas. You came here to learn about the Lattice-Boltzmann method. So what is Lattice-Boltzmann? The original idea of Lattice-Boltzmann was to simulate the lattice gas algorithm. So you could say that lattice gas is already a simulation. Yeah, so this is often what happens in numerics. You do a model of what is already a model, what usually is already a model. So you have hierarchies of models. Yeah. So, and this is a model for lattice gas. And the thing is, we model this statistically. Okay, so what is the original idea? So in lattice gas, yeah, we had many. We wanted to see whether when we use particles, as a very simplified way of seeing atoms moving through air, yeah, on the lattice with a very small number of possible speeds, whether we see emerging on the large scale fluid dynamic behavior. So in order to do this, we have to have a very large lattice, yeah, and we have then to statistically average these particles that are moving around, because you don't have velocity fields or something. You only have the single particles, yeah, and you do statistics over them, and then you see the result. So instead of this, the idea behind Lattice-Boltzmann is that you could solve the statistical problem itself without doing the actual lattice gas algorithm. Yeah. So what you do is you introduce the populations which we call Fi, and this is a probability. It's actually a probability density function probability density to find a particle with the given velocity, so this is the velocity of that particular direction, say we call this Ci, at this particular lattice node and of course at this particular time. So previously, in lattice gas, we have collision rules. So collision rules means particles come in this way, we make them go out that way, right? And now this goes to, in lattice Boltzmann, a collision operator. So here we have some distribution, and we have to change this distribution. And while doing this, we also went back to Cartesian grids. So Cartesian grids. So this was our original Cartesian grid, which we saw that didn't work. Yeah. So the reason was, the momentum, say in this velocity here, could not be moved outside this plane, because when the particle uses this thing up here, I don't know whether you see my point here. When the particle is moved from here to here, yeah, it cannot carry any of its momentum in x direction, because this is orthogonal to x. So what we need is some directions that are not orthogonal to both of them. So we need the diagonal directions. Then it works, but then it does not work for lattice gas, because what we need to do now is, because now we have particles of different or velocities of different lengths, yeah, we have to give them different weights. So it's no longer possible that these can only be ever occupied with one particle. Yeah. So one possibility of what, in comparison to what we had up here, would be then that we have, for example, two particles going in this way, one particle coming this way, one particle coming this way, and we send them back like this, the two like this. Now this will spread momentum laterally. Yeah? So here again, we need collisions between several particles. Just collisions between two particles is not enough. But you see, we need two we now need actually two particles here coming from this side in order to be able to do this. So the way this has been solved is, in the different directions, we have different weights for this. So we, in the later lectures, we'll go through all the theory where we get the weights from. Yeah. Okay. Now, the question that can be asked. So this is the friend Laplace. Is this efficient? Okay, it has been around for 35 years, and you can still fill a small classroom with people. giving a course on Lattice Boltzmann. So I hope you came here because you thought that this is efficient, doing Lattice Boltzmann. Or somebody sent you. Somebody sent you who thought that it is efficient. Or prove me that it is insufficient, that it is not. Okay, I mean, telling you honestly, we're doing Lattice Boltzmann for some 35 years. Not me personally. I'm much older than 35, but 35 years ago I was doing something else. You see, all the others are all still there. It's a little bit like a diesel engine and a petrol engine. So which one is better? You know, they are still both here, right? And the thing is that Lattice Boltzmann is, of course, not necessarily very efficient. It always depends on what you want to do. And there is, always no necessarily. Okay, when I'm by the way, when I'm making a lot of mistake while writing, I'm dyslexic. Yeah, so it's you just do the corrections yourself, or if you don't, if it's so bad my writing that you cannot read it, just ask me. Yeah, so it may not be efficient for very simple problems. So what do I mean by a very simple problem? A very simple problem is in particular pipe flow, right? That is much more. You need 2 degrees of freedom to develop this. Yeah. So discretizing this over its entire length by a lattice and simulating this time dependent may be very inefficient. Also, one of the things that everybody does first with Lattice Boltzmann, lid-driven cavity. Who of you has done lid-driven cavity simulation? You, 2, 3. Okay, a few. So you were waiting until somebody else. Yes. So actually, Lattice Boltzmann is not an efficient tool to solve this problem. Yeah, this is not a good problem for this tool. Yeah, you just use this to see whether you. There are much more efficient ways of solving the same problem, because this problem is simple, and because this problem is usually static. Yeah, that could also be unstatic, but if it is static, then it's not necessarily very efficient. So I have written but. So the computational effort is independent of the state of the flow or the complexity of the flow. So this can be a good thing or a bad thing, right? If your flow is very, very simple, then there are much simpler ways of getting to this simple solution, right? If your flow is complex, then you do not pay extra for the complex flow. Where with many other numerical methods, if your flow becomes more complex, you pay a lot more, yeah, because you have iterations, yeah, so that take longer. Yeah, this is not the case in Lattice Boltzmann. So, you know your tool. If this thing here, for example, implies that this is a good thing for actual turbulence. If you want to study turbulence, because simulating the turbulent flow costs the same as simulating the laminar flow, as long as it is resolved, which is a bit caveat to this, yeah, because laminar flow is, of course, easier resolved than turbulent flow. Yeah, but anyway, for the same resolution, it is the same cost. The other thing is that because we are mimicking nature, yeah, so this doesn't come from mathematicians, this comes from physicists who made these experiments. They could say it's as parallel as nature. Yeah, because we are mimicking nature. Yeah. So what does this mean? The effort always scales linearly with the size of the system. I mean, with the size of the system, we mean the volume of the system. It, of course, does not scale linear with one dimension. Size of the system. So, and just a little bit of theory. What is the difference between this way of doing simulations and more, iterative ways of doing simulations? Is that because we are mimicking nature, we are actually having the same event horizon concept as would happen in nature. So we have this light cone principle. So this is the event horizon light cone principle that many other numerical methods won't have for the entire information that is floating on this thing. So what is an event horizon? So this sounds now like we are doing something relativistic, but this is not what I mean. So suppose this is here our point here, and we have time. Okay, in this context, we'll draw time always downwards and say this here is space, and say this point here is now and here. Then all the information that is influencing this point converges in this light cone. Yeah? So you could say this here is the area influencing the node. And on the other side, you have the other part of the light cone, and you have the area influenced by the node. And since we do one time step at a time, the area from which we are influenced and the area which we influence, these things are very small. So we only ever have to interact with a very small neighborhood. Each node has to act only with a very small neighborhood. So this is, one thing for sure is you have Navier-Stokes solver who have similar properties, usually a little bit different because this doesn't go exactly the same if you have things like Runge-Kutta methods. Yeah, Runge-Kutta methods are not completely time symmetric. Lattice Boltzmann is actually time symmetric, so you can reduce this to one point, so the light cone in one direction is the same as the light cone in the other direction, where in Runge-Kutta methods, the light cone in one direction would be a little bit different than the light cone in the other direction. But if you have something like what is still popular, a fully implicit method, of any kind, and you again have your here and now here, so this again is the time, and this again is the space, and here is where you are. then the area of influence, area influencing stretches out to infinity. Yeah, and the same thing here. Also stretches out to infinity. So, solving the Navier-Stokes equation, can somebody tell me where something like this, where do you have this fully implicit problem? Incompressible Navier-Stokes equation. You are nodding, so. No, the speed of sound would be infinite when we're talking about if you want to solve the incompressible Navier-Stokes equation. Yeah. So when you solve the incompressible Navier-Stokes equation, you would have to come up with an equation for the pressure, right? And the equation for the pressure that you would usually solve is the pressure-Poisson equation. So, I mean, my problem is a little bit, I have no idea on what background all of you are, and maybe you are not on the same backgrounds, yeah? So anybody aware of the pressure-Poisson equation? So somebody is aware of the pressure-Poisson equation, yeah? So the thing is, the Navier-Stokes equation is an equation on the velocity and is on the pressure. You need the pressure in order to solve the Navier-Stokes equation. And the equation that you do this with, which arises from the Navier-Stokes equation under the condition of incompressibility, then basically looks like this. So I get you are familiar with these operators that are also here, our characters. The Laplace operator on P, so second derivative of the pressure, is this strange thing here of the velocity. So one thing that you observe with this equation, it's a partial differential equation because it has all the directional derivatives in it, but there's no time dependence in this, right? So the Navier-Stokes equation, of course, is time dependent, and the time dependence here is not forgotten. It's not that I just dropped it and assumed that it is a static case. The Navier-Stokes equation still is a time dependent problem, but this problem has become time independent. Yeah. So now this is one of the reasons why the Navier-Stokes equation is difficult to solve, because one part of it is time dependent and the other part is not time dependent. So what you do in order to solve this equation is you use a non-time dependent solver for this, a global solver, which has exactly this properties, because it's a global solver. So you need to do this in every time step, yeah, because U and P are functions of time, but this equation does not give you any information about their function in time. Only the Navier-Stokes momentum equation gives you information on of the velocity in time, right? And now you have to globally solve this problem, which means that because it's a global problem, if the size of your system increases, solving this thing becomes more and more and more expensive. So, and this, okay, should I write this down? So we have no time derivative and this leads to the area of influence is basically the same as the simulation domain. This actually, in the pure Navier-Stokes world, this actually leads to the condition that nowadays for large systems, they don't do this anymore, yeah, and they have other ways of solving this equation, not exactly, right, that are faster. So I mean, it's not only lattice Boltzmann gets rid of this problem, but in other ways we get also rid of this problem. So, and by the way, the thing is, this solving the Poisson equation this is a problem of scaling. Yeah, because it can be pretty efficient to solve the Poisson equation, because the Poisson equation gives you real incompressibility, whereas when you use the lattice Boltzmann method, you get only some fake incompressibility if you want this. Yeah. So, and sometimes this fake incompressibility can also cost you a lot of time dealing with this. But this is a scaling problem. So it is, you have to think about this. So if, as long as your problem is small enough, yeah, it doesn't matter whether you have parallelized it or whether it's implicit or explicit, yeah, or implicit may actually be faster. So now you get larger and larger and larger problems, yeah. So this solving something in the entire simulation domain becomes more and more and more expensive. So the gap between using the light cone method and using implicit method becomes larger the larger the system is. But for a small system, implicit may be actually beneficial. Okay, so last point to this introduction is now that we come to the collision operators. So this is something where we will spend a lot of time during this 2 weeks. So we have to start, or say we have to express our elementary collisions statistically, and for this we will use moments. So, okay, what is the idea? Now we don't actually have the particles, we only have the probabilities of finding particles, yeah? And now suppose we have now a given probability that two particles hit like this, then this could be turned into, say, 4 different configurations. So they could go out like this, yeah, turned by 45 degrees. They could be turned by 45 degrees in a different direction, or they can be turned like this, or say they could be turned like this. So one thing that you observe is if they get turned like this, they actually don't do anything, right? This is what they would do if they would just fly through. But this is also a possibility. It's also a possibility. I mean, I can drop this glass of water on the floor and it bounces off and comes back with all the water in it. Is one of the many possibilities how this could go, right? So then, of course, there's not only one collision, but there are all the possible collisions that you can express on a lattice, and they also involve several particles. Yeah, it's a philosophical question what this means. And they go on. So, for example, here we have particles coming from 3 different directions, and they would also collide, and then we would have other particles from other directions, which we would also have to add to this. So now there are different ways to do this, and the art of lattice Boltzmann is in principle in the choice of these collision operators. And so the first one we are going to study will be the one that is according to Bagnaga Cross and Crook. So an Indian and South African and an American working together. It's also called single relaxation time. And actually the idea is from 1954. Yeah, I thought that lattice Boltzmann is much younger than this. So this actually comes from kinetic theory and is only applied to the lattice Boltzmann method. Yeah, the idea here is that you do not care about your elementary collisions. By the way, saying elementary collisions is kind of my own make-up now. Yeah, it's not commonly used here, but this is in the end what it means to do the different operations. So in the Bagnaga Cross-Crook operator, they don't care about how you could split up your collisions. Yeah, they just have a distribution, and they do not care about so they do not have any distinction of elementary collisions. What they just have is a transition of the populations Fi, and this depends on the distance to an equilibrium. So what an equilibrium is, this is what we will learn in the I'm not completely sure that we come to this point, but this is what we will prepare in the afternoon. Yeah, goes like this. So we have, so this will be our nomenclature, that this thing with the star, with the asterisk, is always after collision. So after collision, we have the state before collision plus a rate parameter, relaxation parameter. And here we have the distance between an equilibrium population and the incoming population. So this here is relaxation parameter. Is actually frequency. Okay, now this doesn't distinguish between any different kinds of collisions. Then we have one that distinguishes between them. This is the big class of multiple relaxation. time methods. The thing here is a bit erratic. Multiple, here we express these elementary collisions as statistical moments. So, and this gives us the opportunity to use one independent relaxation parameter for each moment. Now, the thing with this is that a moment, I don't know whether you have had the statistics and know about moments. Maybe this is now a strange moment for you if you don't know what a moment is. So moments, the way we'll discuss about after this course, you will know what a moment is. That's for sure. Yeah? Even if you don't understand Lattice Boltzmann any better, you'll know what a moment is. So moment is always an integral property of a distribution. And the distribution here is the distribution of the particle's momentum. The problem is the integral properties, they can be defined in many different ways. So there is, of course, something that is called the classical multiple relaxation time methods, but in reality, there are now many different methods with different names, which are basically multi-relaxation time methods that use different sorts of moments. Yeah? And moments, so you can differ these moments, for example, by frame of reference. So you can have moments, for example, in an Eulerian, I'm running out of digital ink. Eulerian and Lagrangian frames of reference. Is everybody familiar what that means? What is an Eulerian frame of reference? An Eulerian frame of reference is one that is fixed in space. We also call this the lab frame. Yeah? A Lagrangian frame of reference is the frame that is fixed to the material that you are studying. Yeah? So now you can take moment, you can do statistics in a fixed frame, and you can do statistics in the frame that is moving with the fluid that you are studying. Yeah? And these lead to different moments and actually to different performances of these Lattice Boltzmann methods that come out of them. So then the next thing is these moments are supposed to be, different moments are supposed to be independent of each other. And in order to do this, to make them independent, there are different possibilities. Because, if you think about freedom, yesterday I was walking around with a friend and we were talking about the definition of freedom. And you know that the American vice president came to came to Germany recently and complained that there is no freedom in Germany, freedom of expression or something, right? So, and you know, I don't know, maybe because there are less people carrying guns or something like this. So actually, then because you can have different opinions about freedom. For example, in America, a man cannot take his shirt off in public. In Germany, this is, you know, no problem. Yeah. So you have whatever you define freedom could be different. Then the same thing is with independence. Yeah, independence. You want moments to be independent. But then you have to think about what does this mathematically mean. Yeah? So, and one way, and this has been tried, is to make things orthogonal. I think this is written with an H. And then you find, so make things orthogonal, and then you find that there is different ways of making things orthogonal. Yeah? So there is something that's called the weighted orthogonality. There's unweighted orthogonality, and then there is non-orthogonal things that are still somehow, you know, independent of each other. And then there is other ways that you could cause things to be independent. For example, you could use factorization. And what in the end we will run into is we are using cumulants. Okay, so maybe these things now are potentially not very clear now, but this is what we'll study through the next 2 weeks. Yeah. So then there is one last thing in which they could differ is the adjustment, the relaxation parameter. So you can adjust parameters, for example, that they are physically still accurate, but they are damping oscillations. This is one possibility. So you can use this many parameters to find to make things stable or more stable, going to higher Reynolds numbers. But there is something else very interesting, so-called quadratic relations between relaxation rates. Now what on earth is this? So a quadratic relation means that by combining relaxation rates in a very particular way, you can make the entire method much more accurate. Like you can eliminate leading order errors and make the method much more accurate. Yeah? And this actually is required to go to what we actually want to go to, namely to the high fidelity simulations. So, okay, I spent 1 hour on this. I will very briefly show you a few examples what you can do. So this guy is not my grandfather, even though he looks like him. Is Ludwig Boltzmann, and so the indication is here there's a laminar Boltzmann and there's a turbulent Boltzmann, and we want of course to go to high fidelity, means we want to go to the turbulent Boltzmann. Yeah. So, and this depends, whether we can do this depends to a large extent on the collision operators that we are using. So single relaxation time, I said this is the BGK collision operator, which is very simple. And then there are multiple relaxation time methods, and then there are cumulant methods, which get increasingly more complicated to actually evaluate, but also become increasingly more high fidelity. So say this is roughly what kind of flow we can simulate before it crashes with similar resolutions, right? And by the way, what I have to say is that in these collision operators, they are all equivalent. I mean, at least the ones we are talking about, there's of course some differences in if you want to have something specific like multiphase flow or acoustics or something. Yeah, but in principle, they are all the same. So what is the difference is when you can increase the accuracy of your methods, yeah, for a given resolution, you can do the same thing with lesser resolution. Yeah, so you can of course simulate this condition here also with this method, but you would use a lot more resolution. So it's a question of efficiency, and you know, this is in theory. In practice, in fluid mechanics, you cannot afford, yeah, so to do more, because you will always use what your machine can do, yeah, because fluid dynamics is always under resource. You always have too few resources to do what you want to do. So it's really a practical difference. Okay, so examples that have been done with now this cumulant method is flow through porous media things here with we do urban simulations. This is a part of Basel, and there's acoustic simulations. But I want to start with one example that we just had before, this sphere, which looks like a pretty simple simulation, but which has a certain interesting behavior that was for a very long time difficult to capture with the Lattice-Boltzmann method in particular, because the Lattice-Boltzmann method is an Cartesian grid method. So Cartesian grid method means we cannot easily use a very fine grid at the boundary layer. Yeah, so we can of course refine the grid. Yeah, but other than like in open form, where you have these boundary kind of elements, yeah, where you have very high resolution directly on the boundary, this is difficult to do with actually a Cartesian grid method, because changing the resolution is not straightforward. Yeah, so and therefore this particular behavior that we observe in the flow around the sphere was very difficult to capture with the Lattice-Boltzmann method, and required a special attention. So what am I talking about? If we measure the CD value of a sphere, then over 2-3 orders of magnitude, it will have the same CD value. So you're familiar with the CD value. This is the drag coefficient. Yeah. Also, when you buy your car, yeah, you're interested in this to be low. So this has a very interesting behavior in a sphere, because if you cross a certain Reynolds number, suddenly this drag coefficient drops down by 80%. And the reason for this is in the boundary layer. So you can capture this only if you have the physics of the boundary layer resolved. Yeah? And in order to do this, your method needs to be stable enough, and it has to be accurate enough. Yeah? So it's easy to make a Lattice-Boltzmann method stable, yeah, even for high Reynolds numbers. But what you observe then is that you do not recover this behavior, because the stability destroys your boundary layer. Yeah? So now here we can recover this, and let me show what is the problem. So this is before the track crisis. So this drop here is called the track crisis. You see you have this diverging wake. Yeah? And what happens in this region is just that the vortices become smaller and smaller and smaller. And then there will be, so they get smaller and smaller again, yeah, until this point. And what now happens down here is that they get so small that they kind of forget that they would have to detach here, right? And so the wake that was diverging is suddenly converging, and what you see is you actually had this form track because you have this big wake that is actually sucking on your body, but now your body became narrower because the wake is now completely covered by the body, yeah, and this is why you have this smaller track here. Okay, so this is something that we can do with the high fidelity lattice Boltzmann methods. But 10 years ago, we could not do with the same resolution. Okay, so here's the cutoff angle. Okay, so applications of this in city simulations. So again, this is a piece of Basel. Interesting thing here, if we have a resolution, so we have done this with different resolutions, and I don't know whether I have this on the next slide. If we have a resolution of 1 meter and non-refined grid, then we could do this even 6 years ago. We could do this on a GPU for a domain of 550 by 550 by I think 130 meters. We could do this on a desktop computer with 1 GPU in double the real time if we are just dealing with the flow, yeah, at a resolution of 1 meter. Yes, here are the parameters of this. So wind going in different directions. We have taken Basel because in Basel there is a measurement tower, or there used to be a measurement tower, yeah, where you could, where we have information of the velocity field here, which we could recover, and we also have turbulent kinetic energy, yeah, which in this measurement tower to a certain height, at least. Okay, so this is one thing that you could do, yeah. What I was showing here, hopefully not computation time. Okay, I think that, sorry, the parameters. I think the time was for 3 hours. It's not written here. Okay, I don't. Okay, sorry for not knowing how many hours it was. I remember that if we use a coarse grid and not doing refinement, we were twice as fast as real time. Okay, so this is burning Basel apparently. Last example of this is you can do error acoustics with this, and for this, which I did not bring here now, we have an organ pipe. Like, I don't know whether these things are very common here in European churches. There are these big organs, yeah, and you usually see only the metal pipes which are round, but all of them also have wood pipes. They are a little bit backward, and they have this shape, this box shape, yeah, and the way it works is that they generate a jet. The jet is hitting this edge, and this edge produces an edge tone, and the edge tone must be matched with the resonance tone of the open body, and then you get a sound, and this you can simulate. So usually this requires, so this is a lot of multi-scale problem, because you have to resolve the the tip of this edge. So this is very, very important, yeah, how sharp the edge is. And you want to hear the sound in the room, so you have to get this to the room. So what you end up with is that we use 10, was it 10 or 11? Yeah, level here is written 10 levels of refinement, exponential refinement. So the smallest cell in here is 1024 times smaller than the largest, yeah, so that we can resolve the tip and the room. Okay, so this can be done in Lattice Boltzmann, and then you can measure the spectrum of this. So there is, it's hardly to see. So the orange one was an experiment, and the blue one is the LBM. The LBM is more noisy apparently. So I don't know. I'm probably picking my microphone here and giving the, actually you can recover the pressure field and scale it to the right time. And then you can do this. So when we tested it, it worked. Some of you remember. Sorry for this. Now it's not on the recording. Yeah, so you can make this sound actually audible. Okay, so these are just the velocity fields around this. So two more things. Namely, we also distribute our own Lattice Boltzmann solver. It's called virtual fluids. The reason is, of course, more like we are not selling this, and we are not selling any consulting on this. You are still familiar to download it and work on it, yeah. But because we are not doing the consulting, if you have a question, it may take some days that we answer. Yeah, this is possible. It is more for scientific reasons, of course, that your work has to be reproducible. Therefore, your code must be open. And so this is the motivation then to make everybody use our code. Yeah, and now as potentially the very last thing, but this may take a few moments, is I would encourage you to use this demonstrator now. My institute is called IRMB. Yeah, this is the institute website. On our institute website, we have a link to a simulation demonstrator that's called FlowSim.js. And this FlowSim.js, I've already opened it here, is something that actually my students wrote, and this is using Lattice Boltzmann, and this is running in the web page on your GPU. So it's using WebGL to do the simulation. Yeah, this is done by a student. They made, or by two generations of students actually by now. They made an awesome job with the interface. I have to admit that the code has a couple of bugs. Yeah, as a student work, but it's a very nice. I think is a very nice work. Now we'll take the few minutes that we have to look a little bit and play around a little bit with this thing here. So I just eliminated by pressing this button. I eliminated all the objects that I have here. Here we can distinguish between world coordinates. So we say this is 75 meters, 40 meters. We can turn this, because we are now studying Lattice Boltzmann, we can. So because Zoom is running in the background, it's much slower than it was supposed to. So, it's a Cartesian grid, 400 grid nodes times 750 grid nodes. Yeah, you will be able to adjust here some properties, in particular boundary conditions. So, for example, if you want to do the thing that everybody apparently does first, let's just do this. We can build a lid-driven cavity simulation by putting a no-slip. This is a wall boundary condition here, and a wall boundary condition no-slip here. So we have no-slip, no-slip, no-slip. And up here, we would have to have the horizontal velocity. Say we put the horizontal velocity to 0.1, say. Yeah. Then we potentially want to have this more symmetric. So let's put this to 400. Let's do both 200. 200 by 200. Save changes. So I have to scroll out a bit. Oops. Okay, now this is your favorite lid-driven cavity simulation, in which we can change other things. For example, the viscosity. So if we have the viscosity much higher, then of course we get, the usual, what we currently see, by the way, is the velocity. I guess we can also, do we want to see curl? Okay, it does not, in this case, go back to the velocity. So now I put the viscosity much higher, so Reynolds number lower. Let's make, okay, so this was too low, so it does not like to crash, even though it may crash then anyway. Okay, now at a lower viscosity means a higher Reynolds number, you see potentially more dynamics. So what we are interested in this lecture is different collision operators. Here we have 3 collision operators where I believe that the FCM factorized central moments is potentially not correctly implemented in this. Maybe not a big difference to the cumulants, but we can compare this to Bagnaga cross Crook. Okay, so Bagnaga cross Crook did not survive very long. Yeah? So we can try to make viscosity, the Reynolds number, an order of magnitudes smaller and see what happens. Okay, so when we do it an order of magnitude lower, then it still survives. Make it half of this. Yeah, okay. So you see, I don't know whether you see this very well. Let me see, we'll see the problems, mostly in the pressure first. Now you see some oscillations here in the pressure. It's not very well visible. Going back to the adjustment, let's make this now I want to, they in a sense, they over-engineered this. Let's make this. So, okay, you see, there is, if I restart the simulation, by the way, if you look very careful, then it will not crash everywhere at the same time, yeah, but the crashing will propagate with this light cone thing that I was describing in the beginning. Yeah. So you see, this didn't. There is a difference, obviously, whether we use the simple operator that was already crashing now, or we use the cumulant methods. So cumulant method at this Reynolds number has no particular problems. Let's look at the pressure. see there is no oscillation in pressure. It's already, I think, what was it? What did we start off with 6? So it's kind of 5 times less, Reynolds number 5 times higher than the one where we saw this oscillations. And yeah, I don't know, make it 1 order of magnitude lower means more turbulence. And it will still run. So, okay, so this is a demonstrator for playing a little bit around. You can also, which we have now not shown in particular, you can put some bodies into this, yeah. So you have now a subcavity, if you will. Other more interesting things that you can also move around. Oops, no, this was the wrong. I wanted to pick this. Okay, and then you can play with this around as you wish. So this should be a demonstration that the collision operator actually matters. Okay, so this was kind of what we had for this first lecture. So the second lecture of today in the afternoon will be on the kinetic theory. We're going to derive we will see why time is going one way and not the other way. This is one thing that we'll study in the afternoon, because this is important to understand where the equilibrium comes from that we will be using in order to build our lattice Boltzmann methods. Okay, are there any questions? Is anybody still following me? The relaxation time part. So this here, this omega that we have in this single relaxation time, so there is no, now you can see there's no time in this, right? I mean, I did not explain it in detail because we are going to explain it in detail in later lectures. So I was going to, give the big overview. But the thing with this is, so this omega is a frequency. So the inverse of this would be a time. Yeah. Now you see this is not dimensionally consistent. If this is a time or this is a frequency, but the idea here is like a time integration. So you would have to multiply this by delta x, by delta t, by your time step. So the question is, how much does the arrangement of particles that you find on one lattice node approaches the equilibrium within one time step? Yeah. So when it goes, say it goes directly to equilibrium in one time step, then you would put this here to 1, and then after collision you would have the equilibrium, right? So because these two times are uncoupled, so the time step and the time it needs to go to equilibrium, they are not, they can be independent. Yeah, and for this reason you have this parameter that you can adjust. Yeah, so in the original Boltzmann equation, so so for example, if this is 0, then there would be no collision. In principle, this time here, so this omega frequency is the frequency of collision. So how often does a collision occur? Yeah. So because the assumption that we have is before collision you have any arbitrary configuration of particles that come together. Now they collide, and when they are colliding, they're increasing entropy. They forget how they came into the crash, and they just take up the most probable outcome. So the one with the most microscopic realizations. If you are familiar already with thermodynamics or with kinetic theory. Now, I don't know how familiar you are with kinetic theory. Is this something that you learn? I guess you learn some thermodynamics, right? Okay, a little bit of thermodynamics, but you will. Okay, so in the afternoon we'll learn about kinetic theory, and to that extent that we need in order to study the lattice Boltzmann methods. These methods are explicit in time. Yeah. So you've probably seen on the schedule implicit operators. If this shocked you, come to the lecture, and then you will see that what we call implicit operators is still explicit as an algorithm, in time. So everything, this works only with an explicit method. This light cone thing. You can define that a particle. The Eulerian frame is easy to do in with particles. Lagrangian is difficult with. Okay, now. Okay, Eulerian. So depends on now. This depends on what you mean, what we do with this, because we'll describe part of it with in a Lagrangian frame and part of it in an Eulerian frame. So I think with a Lagrangian frame you mean we are following the particles. Okay, now you have to wait till 2 o'clock, when we discuss what we mean by particles, because the question is what we mean by particles. So if you think molecular dynamics, or you think SPH, with smooth particle hydrodynamics, which for whatever reason is always, you always get there's Navier-Stokes equation, and then there's lattice Boltzmann and SPH. Lattice Boltzmann and SPH are very different things, but somehow they are always put into the same box. I don't know why. So in that case, you're following particles. And here we say that, so the memory says, okay, so it's the particle, I'm this particle, I'm here. So the particle knows where it is. Where here in the Eulerian frame, there is a lattice node, and the lattice node knows what particle it has. So this is the difference. And the big what big difference this makes is that the particle, that the lattice node does not know what particle it has, it only knows how many particles it has. So this makes a big difference in the computational efforts. I mean, it could always say, obviously you're all human beings, but I could also, so you guys, so this is the example that you can easily give. I mean, you guys are all obviously human beings with a good name, yeah, so you will all be different persons. And you are the Lagrangian stuff here, yeah? But we could also describe you, or let's say this, not you, but the room, as a number of chairs which can be occupied and non-occupied, yeah? I just say this chair is occupied and that chair is not occupied, yeah? So obviously this carries much less information than when I look at you as an individual. And so this would be bad for teaching a class, but for doing simulations, it's a very good thing to deal with much less information than, with distinguishing all the particles by their names. And the particles that go in the direct line and the one that's going in the what is this, inclined line, yeah. So there would be more particles there than here. So like in the room, I would always like more people sitting in the front than people sitting in the back. Now, unfortunately, these guys didn't know before that this screen is so erratic, right? So maybe next time they sit there.